Hello, welcome to my talk on Leibniz's invention of calculus. In here, I will talk about what is exactly the Leibniz calculus. Principally, calculus is an evolving thing. As early as in ancient Greece, Archimedes could use the method very similar to the modern calculus to obtain the volume of a sphere. And the significant development in calculus had been made just before Newton and Leibniz. But why we say today Leibniz is one of the core inventors of calculus with Newton? This talk would make an introduction on this. In this talk, I will introduce a brief description of Leibniz's integration of calculus, the definitions and the notations, and some basic rules for calculus by Leibniz, the transmutation theorem, Leibniz's variable transform, the Leibniz integral transform, and I will make also the discussions on Leibniz transmutation theorem. When compared to Newton's calculus, the significant difference for Leibniz calculus is the notation, which are very close to the modern calculus based on the reference here. Or more specifically, the modern calculus mostly adopted the notations of Leibniz calculus. Generally, the Leibniz calculus contains two parts: the differentiation of calculus, which is equivalent to the direct method of fractions by Newton. The derivative is given as dy over dx. And the integration of calculus, which is equivalent to the inverse method of fractions of Newton. The integration is given as this form, the integration fx. In principle, Leibniz calculus is basically a combination of the well-designed notations, basic calculus rules, and the relevant transformation techniques he developed for solving the calculus problem, including the well-designed notations for differentiation and integration of the calculus. Dy over dx is used to indicate the derivative. In Newton's expression, this would be dy over dt divided by dx over dt, or y dot divided by x dot. And the elongated s stands for sum as the integral sign, such as the integral form on fx, the area under the curve fx. The establishment of some basic rules for calculus. One simple example is the differential dxy equals to x dy plus y dx. And the transforms of integration for the purpose of simplifying the integral problem, the transmutation theorem. This is the topic in this talk. Based on the notation of Leibniz calculation from the reference here, the area under the curve y equaling to fx would be given as s as the integration of y. So if we draw this integration, it would be in this form in the plot. The area under the curve y equaling to fx and the limits are from a to b. So this is essentially the method of the infinitesimal method. As we have seen from the plot, the integral of the expression means the summation of all the infinitesimal area, the hatchet area of the small rectangle. In the time before 1660 or 1670s, it might be available if y is a simple power function of x. For instance, y equaling a x power of m. Here m is the positive integer. However, such applications of the integral would be very limited. The main contributions of Newton and Leibniz for calculus were to find different integration method for more generalized curves. For instance, when m is a fraction or a minus value, or y is a more complicated function of x. Because of Newton and Leibniz made the significant advancement in calculus, this is the main reason why people say it was Newton and Leibniz who co-invented calculus. Following the reference, Leibniz drew a tangent line t to the curve y equaling to fx at the point P. See the red dashed line. This line interacts with y-axis at t, and the value of t on the y-axis is z. Now we can draw two similar right triangles, triangle TDP and the small right triangle PRQ. These two right triangles are similar. Thus we have a relation dy is QR and dx is PR. Y minus z would be PD and x is TD. So from this we can solve z given as this. Here we can see z is a new variable. It is a transformed variable from y. And obviously z would be a different function of x. Now we draw a perpendicular line from the origin to the tangent line, and the w is the crossing point, and the distance OW is h. So now we have the similar triangle, the right triangle OWT, and the small right triangle PRQ. So based on these two similar triangles, we have the relation ds is the length of the curve from P to Q. But since here dx is enlarged for illustration, if dx is very small and BQ would be very close to ds on the curve, ds would be the hypotenuse of the small triangle, and z is the hypotenuse of this right triangle. And we will have the relation h times ds equaling to z times dx. Following the method by Leibniz, now we can calculate the area of the triangle OPQ. It is calculated as half of the height h and the base ds, and use the relation as this, so we can obtain the area of triangle OPQ given as half z times dx. So this is the same as this expression from the relation here. Now, following the method by Leibniz, we can calculate all the triangle. See this plot. So all the triangle would be given by the integral of this expression. Now we look at the area under the curve y equaling to fx. It is given as the integration of y. And this area should be equaling to the triangle's area plus the large triangle area delta OBB minus the small triangle area delta OAA. So this expression is actually the area under the curve from A to B. And if we use the two right triangles OAA and OBB, we can have the relation given as this. This is the area under the curve y equaling to fx. And this is the integral on z. This is the triangle area OBB. And this is the smaller right triangle area OAA. And it should be noted in modern calculus, the last two terms can be also given as this. This is basically the Leibniz transmutation theorem. From this expression, we can see the integral on y is transformed to the integral on z. In such a way, we may make the then unintegrable problem into then integrable problem. Even though in modern calculus, such a calculus can be easily established, both Newton and Leibniz had built the method to attack the difficult problem. That's why we say today it is Newton and Leibniz who co-invented calculus. We will see the Leibniz transmutation techniques on how to simplify some specific problem in my talk on Leibniz series. Leibniz obtained the integral transform basically from the graphic illustration. Here we might have a question. Is this correct for all cases? Or can we have some mathematical proof on the correctness of the transmutation theorem? Here in this and the next slide, I will make a discussion on this. So if we apply the Leibniz transform relation into the transformed integral equation, here z is replaced by this function, and we can write the expression as this. So here on both sides of the equation we have the same integral. Therefore, if we put all this together, we will have the expression as this. So the integral on y would be equaling to this minus this. And in the modern calculus, we can write the expression as this. This is, in fact, the integral by parts in the modern calculus. See the details in the next slide. In calculus, we have a relation as this. The derivative of xy would be given as this y plus x times delta y over delta x. We integrate this relation, we have the expression as this. And obviously, the left-hand side term is integrable, so we have the expression as this. We rewrite this equation, we have the expression for the integral on y given as this. And write in a more specific way, it would be like this. This is exactly same as the expression here. Therefore, we prove the correctness of the Leibniz transmutation theorem.